Then you have to draw t minus tau. T minus tau. And then do the convolution.
What's the right units of that? That's not a
It's easy.
No,
That's a snowman.
no, you can actually have two functions of it and then do the convolution of it. You can actually have it be a problem. But actually. Alright, so you can't show it.
I like use that horrible. What's up, Matt?
Okay. Okay, I think there are several graphical examples of convolutions left. Example 9.11, example 9.10, an example something, but I don't think I want to go through them with you. Let me just tell you roughly what they did, okay? Example 9.10. Essentially, if you have something convolving with h tau, you have two rect functions of the same weight. Okay, if you have two rect functions and you convolve them, and if both of them are of the same weight, okay, you get a triangle function. Okay, that is what you should know. This is minus 1, 1. And this is h tau convolved with h tau. Okay, I don't need to work out this for you. Okay, you can do it in your mind. When you convolve them, you get that answer. And then there's another one, example 9.11. Okay, if you have two rect functions that are not of the same weight, or if you have two functions, two rect functions that are not of the same weight, but rank t convolving with rank of t over 2. Okay, so rank of t will look something like this: minus half or plus half minus half, and then rank of t over 2. What do you think the weight is? If this is minus half plus half, what is the weight of the other one? Minus 1 plus 1, very good. Minus 1 plus 1, and then this is how it looks like. And when you convolve two rect functions of different weights, what do you get? Do you get a triangle back, or do you get something else that's different from a triangle? A trapezoid, very good. Okay, you get a trapezoid back. And the trapezoid is actually given in the textbook. Okay, start with minus 1.5, it goes up to 1, and then goes up to 1.5. Okay, let me draw this with dotted lines. Rect t convolving with rect of t over 2. Okay, so I don't think I need to go through that, and you can figure that out yourself. Okay, and then the textbook gives a different way of arriving at the same answer. And you can look through that of the textbook and so on. And then example 9.12, you're given a rect function that looks something like this, 2, 1. And then you convolve with some sort of a strange square pulse, okay, h of t. And when you convolve these two, you can go through the detail, but pictorially you can do in your mind. You get something that looks like this. peaks at 2, and then goes to 0 at 3, and then negative peak at 4, and then go to 0 at 6. Okay? So this is 2, this is minus 2. You can do this graphically in your mind. Unless you want me to go through them, I would rather that you do them yourselves. Okay? So all these are the examples in section 9.1. And if this is okay with you, and then I move on to section 9.2. 9.1.2. Okay? Okay, you've done a lot of convolution, but you actually know the meaning of convolution somewhere. It's just moving two figures, flip one of them, and then look for overlapping integral as you move the two figures across each other and find the integral. But other than that, do you know what the deeper meaning of convolution is? You don't, right? You don't know the deeper meaning of convolution, other than the mechanical steps you have to go through getting your convolution done. So today I'm going to tell you the deeper meaning of what convolution is. Okay? I erase this one, right? How many of you want a cat on the blackboard? Keep it. Okay.
I need it for numbers.
What is the meaning of the cascade sign? It's the meaning of convolution over the cat.
Well, on the homework you get one of those. When you convolve two cats, what do you get?
The correct answer is a duck.
You killed him.
Okay, let's look at what this means. Okay, we learned this before. That if you have a linear time invariant system, then if you have your ft as the input, the output is usually called a yt. Okay? And then the next thing we learn is that if you know how to do this in the frequency domain, then what happens is that if this linear time invariant system is defined by h of omega, then what we learn is that if we have a single frequency going in, a time harmonic signal, what we get out here is just h of omega e to the j omega t. Okay? So, what happens if I have this picture over here? What goes in is not just that, but e to the j omega t. What is the signal that will come out? What would you put in the output of this thing? Times what? Does it need to be multiplied by something? If the input is such, what should the output be? No. I think you're almost correct, but not completely correct. H of omega? Yes? And h of omega times f of omega, right? So the answer, the output will be this. Did you say it?
Yeah.
Maybe you said it in a whisper. You took him and okay, you did not shout it loud. Shout out the answer loud. So this is this.
I modulated it. That's
Okay. You modulate it to the cat's frequency, so I can hear it. So what happens if I have now, I take a linear superposition, a sum of this signal, okay, and put it through this system. At h of omega, I do a sum, an integral summation of this input signal. Okay? What do you think the output should be by the principle of linear superposition? It should look something like this, right? What do I have to add to that to make the output correct? An integral, very good, an integral. Okay, but what is this integral anyhow? This is the Fourier inverse transform of this f of omega, right? So we put the 1 over 2 pi here. What should I put over there? By the principle of linearity, 1 over 2 pi. So this one is actually equal to f of t, right? And what is that equal to?
H of omega y of t.
What?
Oh no.
We don't know what it is yet. Let's just call it y of t. Okay, y of t, which is what we had in the first picture over here. But if you look at the integral, okay, it's the Fourier inverse transform of this thing. This thing should be y of omega. Right, that thing should be y of omega. So you should have y of t translate to y of omega, which is equal to h of omega, f of omega. Okay? So you learn one of the important properties of convolution. If something multiplies in the frequency domain, what does it do in the time domain? So if this is what happens in the frequency domain, y of t is equal to h of t convolving with f of t. That's what you learn. Okay, h of t in this case is the Fourier inverse transform of this function over here. Okay, so you now see the deeper meaning of convolution. Convolution says that if the frequency response of the transfer function is h of omega, it has a corresponding time domain signal, which is defined by this. Okay? The output of this system is just equal to the convolution of the input with the, what I usually call the frequency response of impulse response or systems response. Okay? H of t has a special meaning here. It is just the Fourier transform of the frequency response. This is the deeper meaning of convolution. So it is a way to compute the output in the time domain. So if I have this available in the time domain, then you know how to compute this output by taking the convolution of this signal with that signal. You flip it around, you do the convolution, then you should get the output in the time domain as well. Okay, yes?
So if the LTI is a black box and we give it the left and the right side, we can actually find h of t omega and that h of t is?
That's right. If you know what the output is when you have an input, you actually can divide, take it to the frequency domain, divide and find h of omega is. H of omega will Fourier transform to h of t. Okay, will Fourier transform to h of t, and that is the meaning of what a convolution is. Are there any questions on what this means deeply? Okay. So let's do further and see if we can understand convolution better. Okay, and in order to understand convolution better, this thing is given a name. It's given the name of impulse response, and we are trying to understand why it has such a name. Why it has such a name. So So let's assume a very simple system. Let's assume a very simple system. That I shouldn't maybe erase this, but then if I put a unit step function into this system, okay, my input f of t is u of t, okay, and that this thing has a transfer function or the frequency response which is given by h of t in the time domain, but h of omega in the frequency domain. That thing is described by the same thing, and these two are just related to the Fourier transform. Then I know that the output is just f of t, or f of t convolving with h of t, which is just u of t convolving with h of t. Okay, that is what the output is. Okay. So now, if I know that this is actually my output, okay, y of t is equal to u of t convolving with h of t. Now, if I were to differentiate this equation and ask, what happens if we differentiate it once? If I differentiate it once on the left-hand side, what do I do on the right-hand side? Do I use a chain rule or do I not use a chain rule? Remember you learned something in calculus called a chain rule. Should I invoke the chain rule here or not? Never, never invoke the chain rule. Don't get misguided by the star sign. It doesn't mean multiplication. It means convolution. Okay? Never, never invoke the chain rule. So if I differentiate the left-hand side, what do I get on the right-hand side? Are you Uiuc?
Yeah.
Okay, what do you think I should do on the right-hand side?
I don't know. That's why I asked you.
Oh, you're asking. Yes, Mark.
Do you take the derivative of one of them?
You take only the derivative of one of them. Either one doesn't matter which one, but just either one. So you differentiate it. Very good, okay. You differentiate one of this and convolve with h of t. Or you can choose to differentiate the other one and convolve with h of t. Okay? And convolve with u of t. But what is the differentiation of a unit step function? A unit step function looks something like this. It goes to 1, is 0 here, and then it goes on forever. What do you get when you differentiate this function? You get a delta function. Okay. One way to think about it is that this is the limiting case of an approximate unit step function that looks something like this. Okay, think of an approximate unit step function that has a gradual rise in slope. Okay, that is a precipitous rise in the slope of the unit step function, but you can think of it as the limiting case of this function where delta goes to 0. If you differentiate this one, okay, we differentiate this one, you get something that looks like 0, something that goes to the big value, then something that goes to 0, where this is equal to delta, this is equal to 0. And the height of this is 1 over delta. Okay, and as you make delta smaller and smaller, this pulse hits the roof of this building. It becomes infinitely tall. That is called the impulse function. Okay, the limiting case of delta going to 0. So this is actually an approximation to an impulse. When delta goes to 0, you get this function, which is usually drawn this way, which is called the delta t. Okay, this is called the impulse. And this is called the unit step. Okay. And this is an approximation of the unit step function. So, if I were to think about this becoming an impulse, Okay? If I were to think of that as becoming an impulse, what I have then is that, let me just erase this one. Then I will have the fact that dy dt is actually equal to an impulse convolving with h of t. Okay? An impulse function is an infinitely narrow function that is a limiting case of this function, but it's zero everywhere. So if you were to perform this integration, you can do it two ways. T minus tau, minus infinity to infinity. Or you can write it the other way too, that's fine. The tau, h of tau, delta t minus tau. In both cases, you should get the same answer. Since this function is zero everywhere, except for t is equal to 0, okay, so this picks up only the integration around the thing. So you can think of this being evaluated at t is equal to 0. So I can set t is equal to 0 of this function and take it outside and just integrate this function. This should be a tau, sorry. This should be a tau. So but what is the integration of the delta function? It is the limiting case of this function. This function always has area of 1, no matter how small delta is. So when I integrate that, I always get 1, okay? So this is just equal to h of minus tau.
Excuse me.
Yes?
Why is it direct delta of tau? Wouldn't that be the impulse at when tau is equal to 0? So you just put in a 0 for tau, so you would just have h.
Oh yeah, you're correct. You're correct. Okay? So I get this right. You save my date. Okay? This should be t minus 0. And this should be h of t. Okay? This should be h of t. So if you do it the other way, you save my date because if I do it the other way, I should get the same answer. Okay? So this should be equal to, this function is 0 everywhere except for t equals tau, or tau equals t. So I should set the value of these to h of t. Okay? And take it outside, h of t, tau delta t minus tau. Because this thing only picks one value, and again this integrates to 1, and this is just h of t. So both answers are correct, or equal to each other. Okay? So what it says is that if I were to, can I erase this?
Yes.
Okay, good. Then if I were to have the unit function as my input, my output would be that thing over there. But now, if I have the same LTI, if my input now is just a delta function, okay, my input is just a delta function, which is the derivative of this function over here. And according to this rule, okay, if my input is this, my output to this system should be the derivative of y of tau. Okay, so, but then when I have this convolving with that, when I have this thing convolving with that thing, I always get my output to be h of t. You agree? Can you see that? When the input is a unit step function, the output is this. But if the input now has been converted into a delta function, according to this rule, okay, the output is always h of t. Does everybody get that? Larry, you got that? Yes.
How do we create inputs?
Let's not talk about that, but that's a practical problem. Okay, that's a real world problem. How do you create it in the lab? This is idealized, okay? Idealized. Okay, so input, the response is h of t. That's why this is called an impulse response. Okay, that's why the name impulse response. So h of t is actually equal to the Fourier transform of h of omega. This is the frequency response, and in some textbook this will be called the transfer function. Okay, the transfer function. So are there any questions so far? Yes?
If you just involve u of t with the derivative of h of t, will we get the same thing or we get something different?
What is that?
If you do that.
Oh, this one by the convolution property that we have learned and proven in the textbook. This should give you the same answer. If you don't believe me, you can go and work it out. Okay, but you should get the same answer. Okay, maybe you have to go through all the algebra. It's a theorem. It's almost like a theorem. So if you calculate this way, you get one answer. Calculate that way, you get another answer. But this one should also give you h of t. But this way is much shorter. Okay. So let's see what other things you need to know. An impulse function is actually a very special kind of function that mathematicians did not get used to, because it's a function that's infinitely large. When t is equal to 0, it's 0 everywhere. Okay. Mathematicians have a hard time accepting this kind of function as a function. So this kind of function is called distribution. It was actually first proposed by Uiuc. Uiuc actually proposed this function. This one is actually proposed by Heaviside. So this sometimes is called the Heaviside step function. Oliver Heaviside. Okay? Do you know about Heaviside? Never. Or Ashley knows. What do you know about Heaviside?
Didn't he do something with partial fraction?
Partial fraction? I don't know. I don't know if he did. His name was mentioned in the movie or in the play called Cats. How many of you have seen the play called Cats? Or you're too young for that?
I heard of it.
You've heard of it? Okay. What is that? It's a very famous musical, and one of the lyrics in there refers to Heaviside layer. Okay, if you go through the lyrics of Cats, you'll see his name. It's a layer in the ionosphere, which is due to Heaviside. So if you listen to Cats and then you hear this name, Heaviside, that's him. Okay, it's a very famous guy. Okay.
Wasn't Heaviside the one who condensed Maxwell's equations?
Oh yes, the same Heaviside. Okay. Heaviside also who discovered the way to reduce losses in telegraph wires many years ago. Okay. People call him eccentric genius. Okay, he's an eccentric genius. Okay, so you know about convolution property of delta function. It's actually very simple. So if you have delta t convolving with h of t, you just get h of t. Okay? You have delta t minus t naught convolving with h of t. What do you think you should get? Yes? No?
H of t minus t naught.
Very good. Larry is right. Okay, h of t minus t naught. You forgot one of your convolutional properties. Okay? And I hope I don't have to prove this for you. And also, because of this property that when you multiply a delta function with another function, say t minus t naught f of tau, if you integrate this, what do you think you get? Where does this delta function peak? It peaks at tau equals t naught. So you evaluate the function f of tau at t naught and take it outside the integral, and then just integrate the delta function. So this is f of t naught. Okay? F of t naught, this is called the, I think this is called the shifting property. This is called the shifting property. You know the difference between a shift and a sift, right? What does a sift do? Sift. Sift means you just pick up the tiny thing. So this one actually means that we just pick up the value of this function at this point and evaluate that. Okay, this is the convolution of the shifting property, but also you have this property that since this thing always evaluates to this thing, you can also say that tau minus t naught f of tau is the same as delta t tau minus t naught f of t naught. Okay, this always is the same as that because the two will always give you the same answer when you integrate. Okay, this is called the sampling property. Okay, can you see that this can be evaluated as this because you always take this thing outside the integral anyhow. Evaluate at the peak of the delta function, so you might as well evaluate it beforehand. And this is always equal to each other. Okay. And of course, you know the area property. This is called the area property. That the area under an impulse function is always equal to 1. Okay, so this impulse function, even in the limiting case when delta goes to 0, the area is always equal to 1. This is called the area property. Okay. And then there is this scaling property. Scaling property implies that, let me just erase this. And you know that this is equal to f of 0, right? This is f of 0. What happens if f of t delta, I scale the argument, a times t dt. What is this equal to? Okay, I scale the scaling property, which means that you can probably see it here before you take the limit. Okay, a just stretch the base of the delta function. What do you think it becomes? A times f of 0. Let's see if that's correct. Okay, to see that's correct, then we have to do a change of variable. We do have to do a change of variable so that the two integrals look alike. What is that? Yeah, you're correct. You're jumping ahead. Okay, you're very clever. Okay, so what you do is to put an a over here. Put an a in between here and divide by 1 over a. Okay, so this thing becomes the AT. It becomes the AT. So this integral now is just 1 over a minus infinity to infinity f of t, f of at over a, okay, delta at dAt. Okay, you can write this integral as such. I haven't done anything here, actually I just put in a and divide by a. I put an a over there and divide by a. So these two integrals are the same. Now I can call my new variable t prime is equal to at. Okay, then you can see that this is 1 over a. The limit of integration is still infinity because this doesn't change the limit. This is 1 over a t prime, delta of t prime, dt prime. So what does this evaluate to? F of 0. So Georgie was right, okay? It's f of 0 divided by 1 over a. Okay? So that is a scaling property, which means that if you scale, okay, if you scale, then you have to account for this kind of property that delta of at behaves like 1 over a delta of t. Okay, it behaves like that. Okay. But if you're not sure, you just do a change of variable to make sure that you're on the correct track. So it might be a little bit trickier if I don't do this evaluation at a t minus tau, t minus t0, say. If I do it this way, then it would be a little